In this module, we want to talk now about definite integrals. So module 10.1 was about indefinite integrals, basically that process of working a derivative backwards. Definite integrals now is going to be a little bit different. We're going to have similar concepts, but instead of our final result being some function plus a constant c, whenever we calculate a definite integral, our answer is always going to be some real number. So we're going to get to a resulting number rather than just a function. We're also skipping around in the textbook a little bit now. We're jumping ahead to eText section 6.4 and 6.5. Some of the content that we're skipping, we're going to go back and cover, and then we're going to pick and choose, highlight some different topics from 6.4 and 6.5 that we want to cover now. There will be other examples from these sections that we're not ready to handle yet, but we'll come back to those a little bit later on. So, what we want to talk about with definite integrals is first the idea of approximating areas. So whenever we calculate a definite integral, really what we're trying to find is the area between a curve and the x-axis. So before we get into figuring out how we do this exactly, let's take a look at how we could try to approximate some of these results. In particular on the curve below, over the interval from 2 to 5. So essentially what we want to find here is the area under the curve between x equals 2 and x equals 5. So we want to find the area of this shaded region. So we don't have a technique to do that exactly. This isn't any kind of nice geometric shape. It's not a rectangle, triangle, anything like that. But what we're going to do is start off by relying on older formulas that we have. In particular, we're going to look at first using the area of rectangles in order to approximate our area. So the area of a rectangle can always be calculated as length times width. So what we're going to do is take advantage of that idea in order to come up with an approximation for the area under the curve. So we can do this a couple of different ways. We know that we're interested in the area between x equals 2 and x equals 5. So what we can do is break this into rectangular regions and then find the area of each of those rectangular regions to come up with an approximate for the area under the curve. One way to do this is to use a left endpoint. So meaning our first value here would be at x equals 2. So we would start at x equals 2 and draw a line straight up until we intersect the graph. And then from there we'll draw over to finish off that rectangle. So then the question becomes, how many subintervals do we want to use? So let's start off with a really simple case. We'll use one interval. So we'll take this range of values from 2 to 5 and we'll break that into one interval. So we'll just consider this as one complete interval. So this is a rectangular region that we started at x equals 2, traced up to our function value, and then basically turned this entire interval into one giant rectangle. So obviously we have a couple of problems here, or one major problem, and that being that we have this region in red that we're completely missing. So we're going to find we could find the area of this rectangle by figuring out the height of this rectangular region, multiplying that by the width. That would come up with an approximate, but we've got this huge region that we're missing out on. So another method is, instead of using left endpoints, we could look at the right endpoint for each interval. So if our interval is from 2 to 5, 5 would be the right endpoint of that interval. So we would start from that right endpoint and draw a line up to our function value, and then finish off this rectangular region. So we have an issue again here. In this case, we've got a lot of area that we would be calculating that we're not interested in. So if we find the area of this rectangle, we're finding that region below the curve, but also this area above it that we're not interested in. A third tactic would be to use the midpoint of our interval as the basis for setting up that rectangle. So the midpoint between 2 and 5 would be about 3.5. So instead of drawing our rectangle up from the left endpoint, right endpoint, we would draw it up from the center until we hit our function value. And then we could, again, close off this rectangle. So in this case, we still have a little bit of area above the graph that we're including that we shouldn't be. And we have a little bit of area below the graph that we're not calculating, but we should be. But in general, what we see is whenever we use this midpoint method, we're going to have less error in our calculations. There's going to be fewer regions that we're not taking into consideration and fewer regions that we're taking into consideration by mistake. So in this case, the first two, we've got a large amount of error. Even in this last example, we've got two relatively large areas that we're considering. So let's go back and try to improve these approximations. So now what we're going to do is in each case still consider that range from, or I'm sorry, the domain from 2 to 5, that interval from x equals 2 to x equals 5. But now what we're going to do, instead of using just one subinterval, we're going to use, we'll break this up into one subinterval from 2 to 3, a second subinterval from 3 to 4, and a third subinterval from 4 to 5. So now we're going to break this up into 3 separate subintervals. So if we use that left endpoint method, 2 is the left endpoint for our first interval. So we'll trace up till we hit our function value. 3 is the left endpoint for our second interval. And 4 is the endpoint for our third interval. And then we'll again close off each of those rectangles. So now we still have some area that we should be considering, but we're not getting as part of our approximation. But by increasing the number of subintervals from 1 to 3, that amount of error has been reduced quite a bit. If we look at using the right endpoint method, now 3 is the right endpoint for that first interval, 4 is the right endpoint for the second interval, and 5 is the right endpoint for the third interval. And then again, we can close off these rectangular regions. So here, again, we've got an over approximation. We're including some areas that shouldn't be in our calculations. So the left endpoint, right endpoint, we're always going to end up with a little bit of an over approximation, a little bit of an under approximation. But again, using more subintervals is leading to a better approximation because we have less area that we're considering that we shouldn't be. And then again, we could consider this using that midpoint method. So we'll use the midpoint of each interval. And then close off each of these rectangular regions. So that first interval is still from 2 to 3, but we're using 2.5 as the midpoint to see how tall that rectangular region should be. Second interval should still be from 3 to 4, though it looks like my drawing got a little sloppy, and from 4 to 5. So again, what we see is we have a little bit of error in each case because we have some sections we're including that we shouldn't be, some sections we need to be including that we're not. But again, this midpoint method is always going to give us, typically going to give us, our best approximation. So to summarize all that, if we talk about this idea of making approximations using these rectangular regions, there are a few observations we can make. So the first is that anytime we use these approximations, there's always going to be some amount of error. Obviously, we want to control that as much as possible, but anytime we come up with approximates, we're going to be off by a little bit. We can reduce that error by using more subintervals, which we saw above when we started off with one subinterval versus now using 3 subintervals. We have less error. And we can also decrease that error by using the midpoint of each subinterval. So using the midpoint for the subinterval typically gets us the least amount of error, and the more subintervals that we use, the better. So we jump from 1 subinterval to 3. If we increase this to, say, 10 subintervals, 100 subintervals, 1,000 subintervals, that approximation is just going to keep getting better and better and better. So as we move forward to actually calculating definite integrals, the idea that we want to think about is breaking this up into these rectangular regions, but having that number of subintervals n approach infinity. So this gets back into the idea of limits. We can't actually draw an infinite number of rectangles. We can't calculate the area of an infinite number of rectangles, but the idea that we're going to be going for is increasing this number of rectangular regions, getting more and more and more until n is significantly large and particularly approaching infinity.